So again, this question is going to ask you to do a lot. I'm going to need your help because I can't read it. In a lab neutralization, reaction is conducted between what? Okay, 4.5 molar hydrofluoric acid. So let's start right there. So I'm going to write HF. I want you to conserve your space. So HF, and it says it is 4.5 molar. Okay, and 3.2 molar barium hydroxide. So I'm going to say plus. Now, what is the chemical formula for barium hydroxide? Very good. Ba parentheses OH2 because barium's a group 2. And then it tells you it is 3.2 molar of that. How many grams of the salt product? So what they're telling you is going to be produced is a salt product. Now, the problem is that you need to kind of understand what they're asking you. Since what unit are they asking you to find the salt product in? Grams, which means that what state of matter should it potentially be in? Solid, very good. So what we've got to figure out is what the salt product is going to be. Now, my first question to you is, if I wrote this up there, just like this, hang on one second. Way down there towards the bottom, it's like the third from the bottom. If I asked you what type of reaction this would be, what would you say? No. It's an acid base. Very good. Because this is an acid and this is a base. Because it said in a neutralization reaction. Okay? Now my next question is one of these strong? Which one? This is a strong base, and what is hydrofluoric? It is weak. Remember we talked about that. There was two reasons. One, it was too small, and the other one was high fluorines to electronegative. So we've got a weak acid plus a strong base. Now, what we're going to get into next week is we're going to be talking about net ionics, and we're going to talk about how this is actually really going to look. But let's just talk about it from the standpoint that we know as of right now. So what would be the salt product from this? Very good. BaF2 solid. BaF2 solid. And what else is going to also be the product? Very good. Now that is something you should know, because every time last year we had a acid-base reaction, what were the two products? A salt and a water. Very good. Is that exactly what we got? A salt and a water. Now this year, the new concept is there's going to be two of them. We're going to have to write this in net ionic, and we're also going to have to understand that some of the salts that are produced will perform a what? A precipitant. That's what, because all acids and all bases are in what state of matter? Aqueous. So do you agree that we took a liquidy thing and we took a liquidy thing and we poured them together and something solid fell out of it? That's exactly what happened here. So here's the question. How many grams of the salt product would we form? So do you agree that here is our question? Yes. This is an interesting conundrum. Conundrum? Look it up. How many grams of salt product would be theoretically? Why is this word interesting? That is what you should mathematically create. If you did this experimentally, could it be different? Yes. I'm going to throw this at you. Should it ever be more? No, that's like getting more than 100 on a test. Eliminate bonus points. Okay, we're not talking about bonus, we're talking about physically, can you earn more than 100? No. So again, you shouldn't earn more than you theoretically should produce, unless your math is wrong. If you combine 455 milliliters, so I think I'm getting dyslexic, milliliters of this stuff, and with 672 milliliters of the barium hydroxide. So, what is problem number 1? All right, let's actually start there. Let's balance it. Is it even balanced? I didn't even pay attention to that. It's not balanced. So let's start there. So I need a 2 here. That gives me 4, 4, and so I need a 2 there. True? So 2, 1, 1, 2. By the way, if you don't know what I'm talking about when I say 2, 1, 1, 2, I'm just calling out the coefficients in order as they would appear. So 2, 1, 1, 2. And again, some of you haven't had me, so that's just my methodology of that. So now, that's really important. I'm so glad you said that, because we would have been screwed if we didn't do that. So now, what is our next major problem? Okay, very good. That's the key. Which one of these is going to limit how much salt I can produce? I got to find the limiting reactant. Now, I've given y'all that little cheat. What was that little cheat? Okay, limiting reactant is equal to moles over the coefficient. So I'm actually going to use this page because it goes a little bit faster. All right, the HF, and I want you guys just to continue working underneath it. HF, it was, first of all, how do I get moles out of molarity and volume? Okay, moles equals molarity times volume. Okay, so HF was, what was the concentration? 4.5 molar times the volume. Be very careful. 0.545 liters. Why did you have to change it? It was in milliliters. Very good. So here's what I need you to do. I need you to calculate how many moles that would be. Please don't yell it out loud. Actually, find a calculator and do it, because I feel like some of the biggest problems that students have in this class is they watch me do everything and they never do it for themselves, and so you don't know what you're doing when you actually have to do it. So I want you to calculate this stuff. Yes, ma'am. You can come get one of the yellow ones. No. This is not honors chemistry. You've got to learn how to use the graphing ones. They're what? It does the same thing. It was. It was recording. I can email it. I have proof. Hope you're never president one day. No. Alright, so what is the number of moles? Alright, so I've got 2.5 moles. By the way, is this a fairly potent acid? That concentration of HF, yeah, HF is extremely dangerous. Now, one thing I just want to throw this at you. Please do not assume that all weak acids are safe, because that's very infactual. Okay, some of the weakest acids are actually the most dangerous. So don't correlate strong and weak with dangerous versus safe. Those two things do not correlate. Remember, strong and weak are defined as only and what only? 100% dissociation, percentage of dissociation. So strong is 100, weak is anything less than that. You can't define dangerous and safe on those terms. That one. In fact, it's so dangerous they won't even allow it in high school chem labs. Okay? Alright, so we've got that. And so the next one is, this isn't hydrochloric. Yeah, it's right up there on the counter. Sulfuric. Which is also very dangerous, but it's strong. Okay? Alright, so what was the concentration of barium hydroxide? Alright, so 3.2 molar times the volume. 0.672 liters, which gives us, and again, don't yell it out loud, everybody have a chance to do it. So 3.2 molar times 0.672 liters. This gives you what moles? So 2.2 moles. Now, if we go back to our balanced equation, it was 2, 1, 1, 2, right? So what do I need to do to the HF? Divide it by 2. What would I do with the barium hydroxide? Divide it by 1, which gives me what? It was 2.5 divided by 2. Thank you, ma'am. So I've got 1.25 here, and I've still just got 2.2 over here. So that tells me what is true. HF is our limiting reactant. That's 1.25. Okay? Does that make sense? So all we've done so far is we've converted our concentration of volume to moles, and then what did we decipher from that? Our limiting reactant, right? We cool with all this so far? Is anything we've done so far brand new? No, everything's the same. So, now that we know that this is our limiting reactant, and we have decided, what was the moles again for me? The number of moles. It was 2.5 moles. So, I'm trying to get from HF to what specifically? BAF2. You with me, Claire? You sure? Okay. So, I'm trying to get from here to here. What units am I going from and to? Can you do that? I would hope so. Okay. So, yes, sir. True. Because technically it would be 2.5 Z. No? It'd be 2.5 because the concentration they gave is 4.5. So it's 2. That's fine. Yeah. Alright, so I've got 2.5 moles of HF. Okay. How do I get from HF to barium fluoride? Mole to mole. So I've got mole of HF to mole of BaF2. And then I got to go one more step. So I've got mole of BaF2 to grams of BaF2. Now, what is your mole to mole ratio, top to bottom? It is 1 divided by 2. Now, where do grams come from? How do you get the number? The periodic table, right? I want you to calculate the mass and don't say it out loud. Barium's mass is 137.33 and fluorine is 19 even. So fluorine is 19 even and barium is 137.33. So calculate the molar mass of barium fluoride. You get 165.33. I forgot to carry the 1. That would help. Thought I did that wrong, but that's okay. We all make mistakes. Alright, so wow, that's not what I want. So 175.33. So then what would you do mathematically? Multiply and divide. So 2.5 times 175.33 and take half of it, which gives you a grand total of 219. Let's stop right there. What's the decimal number? 0.1. So just 219 because we need 3 sig figs. So 219 grams of barium fluoride. Yay, nay? Okay, good. Logically, does it make sense? Okay. Did I do it a different way in the video? Or is this how I did it? Okay. 175.33. Oh, we're cool. We're cool with that. Because what I was doing as I was looking at this problem, I was thinking, is there another way to do it? And I wasn't sure. And so what I wanted to do is I wanted to have a little fun with this problem. And what I wanted to do is I wanted to do exactly what we did with the last problem we did the other day. Is when we poured this. No, that's not possible. It's not. Yes, that's the issue because they're going to neutralize and the moles will not be the same. Yeah, so that's okay. So I can't have that. All right. That is so not true. Okay, I'm going to show you all that in a few minutes. Okay. Same exact one. I need to add a catalyst. That was the problem. Okay. Which does what? Speeds it up. We're going to talk about why it speeds it up as well. Alright, what I want to do is I want to double check. I want to go through something else. I gave you these sheets the other day whenever I was out. Hopefully you still have them. So this is what I want you to take out. So as you're finding them, I'm going to go get that little demo, which is where we're getting at the end of this chapter. So let's talk about what's really going on. I told you that blue solution that we're using is what specifically? All right, so you told me it's copper 2 sulfate. Now, where are my 2's? Why are there no 2's? Copper 2 plus and sulfate is 2 minus. But you also told me that this is in an aqueous format, true? So for something to be aqueous, what does that mean about the solution? You hush. Somebody else. Really, when we say aqueous, we really mean that plus H2O, right? So what has that water done? It's ionized the what? The ions. It's ionized this. So really what we're saying is in solution is what's present. The copper 2 plus and the what? The sulfate ion. So these are the two things that are floating in that blue bottle, along with what else that we don't really talk about? The water. Okay, the water is creating this solution. So what did we react it with? Plus, let me actually cut just one more. Okay, plus 1. Can y'all see that color? Is that too dark or too light? I don't like that. Let's make it black. Okay, so plus aluminum. So here's the deal. So we've got copper reacting with aluminum, right? Now, I added a catalyst. And what was that catalyst? HCl. Okay, and I'm just going to put that above the air because that's where all catalysts go. It just made it happen a little bit faster. The HCl has nothing to do with the reaction except making it happen a little bit quicker. Now, in the end, we see something. What did we see specifically? We saw color change, we saw heat and light, but that color change wasn't due to a color change of the aluminum. What was actually happening? It was changing forms. What was this aluminum doing with the copper, or vice versa? What was the copper doing with aluminum? It was swapping places. So we no longer have aluminum solid, right? We now have what forming? We now have copper solid forming, which is causing what? The color change. So when you see brown, you assume the aluminum has changed color, but that's not true. What is actually being produced that caused the color change? The copper is actually being changed. Okay, so if we have aluminum solid, what has to happen to the aluminum solid to be able to react? What has to happen to it? What does it have to do? So it can't be solid anymore. What does it have to turn into? Aqueous, which is more or less, we call it the ion, right? Yes? So now we had copper ion turn into copper solid. And we had aluminum solid turn into aluminum ion. But the interesting part is, where did this sulfate go? Did it go anywhere? Is it still there? Is it still floating around in that bubbling bubble? Or that bubbling beaker? So we still technically have the sulfate ion floating around. It just doesn't disappear. Okay? So here's the next concept that we need to talk about, and it's another type of reaction. And you've heard me say this one before. And it is called a redox reaction, which really needs to be split in half. Excuse me, that's the wrong place for my half. It's redox, red ox. What does red stand for? Reduction. Okay? And what does ox stand for? Oxidation. So really this is just a shortening for reduction oxidation, or redox reactions. What you guys have got to learn is what is going through what. Can you have one without the other is the key question. No. When you have reduction, you have to have what? And vice versa. When you have oxidation, you got to have reduction. So what you guys have got to understand and learn is which one is going through which. Let's start with the easy part first. In math class, what can you do with like terms on opposite sides of the problem? Cancel them out. We're going to pretend that this arrow is like the equal sign. Is there anything that are like terms? Why is sulfate the like term? It's the exact same. Did it change forms? No. So we're going to get rid of it. We don't need it. In chemistry, we have a special name for those things that hang out and watch and do nothing for the reaction. Very good. These are what we are going to label as our spectator, but what specifically? Very good. These are our spectator ions. Okay. So the next progression we're going to get to next week is what we call net ionic equations. So let me ask you something. In math, if you cancel them, is there a reason they're being canceled? Why? They serve no purpose of being there. So if the spectator ion has no effect on the overall reaction, is there really a purpose for it being there at all? No, there is no purpose. So we can eliminate the spectator ions. We're going to talk about how we can do that. So the part that we really need to focus on is this redox part. Is what is being reduced and what is being oxidized. And it's kind of a tricky play because of how it works, but I've got a really simple way to do it. And we need to focus on this reduction part. What does reduction mean in your mind? To lose. But to lose what specifically? That's the chemistry part that makes it difficult. When we think of reduction, we think of values that are decreasing, right? So let's focus on copper for just a second. So copper's oxidation state. And this is a new little fact that you're going to have to learn. Copper went from a what state to a what state? All right, you're thinking of states of matter. Oxidation state. It went from a 2 plus, and this is the new little fact that you need to learn. We know that it's 2 plus because it's obvious. What is the oxidation state of a solid neutral metal? 0. So copper went from a 2 plus to a 0. Did that value go up or did it go down? It went down. So technically we can label this as what process? Reduction. Now, here is why the chemistry makes it hard. What is it actually atomically doing? It's gaining electrons. That's the hard part. So if you look at it from the electron standpoint, it's actually becoming more negative, which is weird, but that's the difficult part. So if you look at it simply from the numerical aspect, it's simple. But if you look at it from the chemistry part, it can be confusing. So this is why we have the acronym. Hold on, I just lost it. Yeah, oil rig. Thank you. Totally just went blank on that. And some of you have heard this, and some of you this is new, but some of you this is a good refresher. So oil rig. So oil is, or rig is, reduction is a what? Gain. But a gain specifically of what? Electrons. Okay? So now let's look at the other concept. Let's look at the aluminum. Aluminum is going from a solid thing which has an oxidation state of what? 0. So it's going from a 0 to a what? 3 plus. So numerically, what's it going from and to? Or excuse me, is it going up or down? It's going up. And up is oxidation. Okay, so this technically is the oxidation part of it. But atomically, what's happening? Losing electrons. How many? 3. So that's another aspect that we're going to talk about. So technically, it oxidized 3 electrons, and technically, copper did what? It gained. So this was minus 3, and this was plus 2 electrons. Is that a problem? It needs to be balanced. Thank you, Charles. Okay. So let's look at this one more time. So what I'm going to do is I'm going to eliminate the sulfate. So I'm going to rewrite this. I'm going to write it as copper 2 plus Al solid yields copper solid plus Al 3 plus. So if we go back and we look at this, can we balance it? Can we? Because there's something new, and this is the last part that I'm going to add new. Do you agree that we always have to make atoms balance? Do you agree with that? And what that means is if I've got one Cu, I've got one Cu. The second thing that we always have to have balance is the charge. But the third thing that's new is the electrons. Because but charge and electrons are kind of one and the same, right? So if we look at this, we've got copper 2, copper 0, aluminum 0, and aluminum 3. Do our atoms balance? But does our charge? That's the aspect that we have to figure out. So how can I make our charge balance? What is my total charge on the left-hand side? What is my total charge on the right-hand side? The entire side. What little mark? It's 0. Means, and I really should have put it right here, which basically means it's neutral. So I see a rule that can be applied. 2, 3, 6 rule. Huh? That's a problem. But is that okay? Because they're neutral. Exactly. So now I've got 3 coppers and 3 coppers. True? I've got 2 aluminums and 2 aluminums. Now, what is my total charge on the left side? What is my total charge on the right side? So it's balanced. But I'm going to make this really, really easy when we get into redox reactions. I did it using my brain. I'm going to teach you mathematically how it works. Okay? So again, seeing this is the progression that I'm going to need you to get to. But logically, does it make sense? Charles, is it simple? It really is, I promise. Okay? It's really easier than it looks. Because everything we did was just looking and moving and playing. When you actually break it down into what we call half reactions, it's really simple. Okay? Do you need me, Charles? Do you need me? Okay. Alright, so the one right here, let me pause the video. I want to send something around. This is how we're going to tie all this in. It's because I want you to see why are y'all so fixated on drinking chemicals, touching chemicals, or wanting things to blow up? You're so fixated on those 3 things. Can I drink this? Can I eat this? Can I touch this? It's chemistry. No. Okay. I guess. Sure, Nick, go ahead, drink it. Sure, go ahead. No, it's not. You're the dummy who drank it. You signed a lab safety sheet stating that you would follow the rules of the lab. And what is the rules? No eating or drinking. I didn't say, I didn't say drink it. I said if you want to. I know that. Okay. Shh. So here's the thing that I want to talk about. Number 1, show how each of the strong electrolytes. Let's pause right there. Number 1, let's focus on this word because this is the key word. Strong. What does that tell me by definition? 100% dissociation. So you should know that as soon as you see the term strong, there's another word that you need to begin thinking. And it's, no. What did you say? No. Soluble. Okay? As soon as you see strong, you're going to connect it with 100% and you're going to connect it with soluble. Because if it's strong, does it have to break down? All of it does. You can automatically assume that it's soluble. The second thing is the term electrolytes. Now, I've asked this question. First of all, there's two questions I'm going to ask. Listen to how I ask it. What is an electrolyte? What does it do? It conducts current, doesn't produce. It can if you have it able to be conducted, which is a galvanic cell, which we'll talk about in electrochem. But an electrolyte produces current. How? Excuse me, conducts. See, you got me off. It conducts current. How? Ions. Okay. So now we've got soluble and we've got ions. Guys, y'all stay with me, okay? See, this is why I can't do anything cool, because y'all can't just... So, guys, y'all, please, 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 please. So we've got strong electrolytes that break into its component ions upon dissolving in water by drawing molecular particulate levels. So the first thing I want to do, there's two things you were supposed to do, and I put this in the instructions, and I've written on yours. Mine doesn't have it. Show how each of the strong electrolytes break into its components. So the first thing I want you to do is to figure out what are the components, because if you don't know what the components are, then you can't figure out how they work in the solution. So let's take calcium phosphate, for example. So since we know that calcium phosphate is soluble, which you're going to learn solubility rules starting next week of how you would know that it is soluble, okay? Because there are reasons for all of these, and if you don't know your solubility rules, you won't be able to understand this. But what its parts are. So calcium phosphate has how many ions? It has 2 ions. What are the 2 ions? Calcium, which is what? Calcium 2 plus, and what other ion? Phosphate, which is PO4 3 negative. Now the key here is, for every 1 calcium phosphate, how many calciums are you getting? You're getting 3. For every 1 calcium phosphate, you're getting 3 calcium ions. How many phosphate ions are you getting? You're going to get 2. So if I take this and I throw it into some water, for every 1 calcium phosphate that hits that water, I should get 3 calciums and 2 phosphates. Okay, so let's look at the next one. B. Did you pour that out? Okay, good, thank you. So now I have potassium what? No, the name. Nitride. Remember, you eyed by yourself. There's nothing there with the N, so it's by itself. So potassium nitride. So we have K plus and what? And 3 negative. Very good. That's very important, because if you don't get that right, it's wrong. Okay? Obviously. So how many Ks would you get out of this? 3, and how many Ns would you get? 1. Very good. And then the other 2, let's just do them just for... We're going to get Fe what? What charge? 3 positive plus Cl minus, and you're going to get 3 of those. And the last one, you're going to get Sr what? This is the good one. 2 plus. Very good, because some people are going to want to put 1 plus and 1 minus, but you've got to know your charges. So CO3, 2 negative, but you're only going to get what? 1 each. Okay? So, yes, ma'am. Yes, ma'am. They do matter. Absolutely. So let's talk about this one. So what is the total charge right there? Positive 6. What is the total charge right here? Negative 6. And remember, we're going to use the arrow as the equal sign. So positive 6 and negative 6 make this side neutral. What about that? There's no charges, so it's also neutral. You see what I'm saying? Okay, that's actually a really good question at that point, because we did talk about that. So there's a lot of positive negatives over here, but they're the same amount, so it has to cancel each other out. Same thing with this. There's 3 pluses and there's 3 negatives. So they cancel, making it neutral. 3 positives, 3 negatives, 2 positives, 2 negatives. All right, so now let's go on to the next part, which is drawing the molecular level pictures. Charles, last year on the AP exam, was there a picture where you had to draw water around an ion? Say yes, there was, okay? And I've actually already showed you this. So this is how simple this could have been. And as a matter of fact, the interesting part, the ion that was chosen in that particular problem was the calcium 2 plus ion. And it asked you in that question, how many water molecules? Quattro. But specifically, how did we draw the water around that thing? Okay. We're going to put the oxygen next to it, right? So we're going to put an oxygen here, put an oxygen here, put an oxygen here, and an oxygen here. But if I draw it like this, is it right or is it wrong? Why? Okay, well, yeah, I'm fishing for something else. I'm actually going to bounce out here. And I know your space is very limited, but that's okay. So then let's actually finish it. Okay? So what would you then add next? You add a phosphate. That's definitely not a plus. So how would you draw this one? All right, so we got hydrogen. So we've got 1, 2. And guys, I'm going to be lazy, and I'm only going to draw 3 waters around it just for space. Just do what the question says. If you left it like this, would you earn full credit for this problem? Why? I only have 1 calcium and 1 phosphate. Is this the correct ratio for this compound? No. I need how many calciums? I need 3 calciums. So I need to change this to calcium, 2 plus, and I'm going to cram it in up here. I need another one up there. So what I'm going to do is I'm just going to write W, W, W. Don't ever do this on the test. I'm doing it for time and space. W, W, W. W stands for what? Water. Absolutely, they'll give you no space. Yes, they'll give you no space. And the second thing I need to add is what? Another phosphate. And I'm going to label it W, W, W. And again, I'm begging. What's wrong? You can, yes. That's getting a little lazy. So again, but what I want to make sure that you understand is one of 2 things. Number 1 is that you understand the ion-to-ion ratio, because if it's not correct, it's wrong. And the second thing is the orientation of the water molecules. What does orientation mean? How they're arranged. So if it's positive, what part of the water? You've got to have the oxygen, and if it's negative, you've got to have the hydrogen. This right here should have been drawn 2 more times for calcium and 1 more time for phosphate, exactly like that, to get the correct drawing and the correct representation. Okay? All right, so we're done with that one. So let's go on and let's look at one of the questions. I love this first question because it jumps right off into the deep end of making you think, for one simple reason why. Calculate the molarity for 184.6 milligram sample. And enough dissolved water to make 4.33 milliliters. This is the kind of junk that they would do to you. They're seeing if you're paying attention. What is the actual question? Calculate the molarity. If you make it dummy proof and you say, well, they're asking me for molarity, what is molarity? Moles over liters. Well, I've got to get both of those units. Is anything they gave us able to be plugged right in? No, and that's where they're going to get you. They're not going to give you things that are that simple. Real quick, what would you do first? All right, so let's do the liters first because that's easy as 4.33. But what would you do with the 184.6? Convert it to grams and then do what? Then moles. Don't use 184.6 milligrams and go into grams or go into moles. You can't do that. Okay? You guys, will have a great weekend. We'll see you on Monday.